Hello all, welcome to our next project, audio classification using neural networks. So now, in this project, we'll be understanding about how we can use machine learning in order to classify our different audio files. Like suppose what we'll be doing is basically if you're hearing a cat voice, you know that that is a cat voice. But how does a machine tell us that? If a machine or a computer hears a voice, how it can tell that okay, what is that voice? What is that voice? Similarly, we can do much of several things. So now in this project, we'll be understanding the same. So as written, during the course of this project, we will learn about classifying different audio files on the basis of their labels using neural networks. This project will give us a brief idea on how machine learning is applied in audio files. So, as moving forward, now, what is audio classification? What is this thing? Now, audio classification or sound classification can be referred to as the process of analyzing audio files. So now basically it is kind of a cluster making algorithm, like if you have different data points in a cluster, and what do you do in a clustering or classification algorithm? You find out the number of clusters which are similar to them, and you assign them into one category, right? So similarly we'll be doing the same in this also. For instead of data points, we'll be having some audio files. We'll be having loading some audio files, we'll be extracting information from it, like the different features. Then we'll be using those features as our independent features and that label as a dependent feature to basically do the classification. So now audio classification is the process of listening to and analyzing audio recordings, also known as sound classification. This process is at the heart of a variety of modern AI technology. Yes, as I said that this technology has been used all over the stream and all over the country. There are several different applications which uses audio classification, like virtual assistant, automatic speech recognition. We'll see those the different definitions or the application in the next slide. But by this time you have an idea about what audio classification is. So now moving on to the applications. So as I said that there are several number of applications, audio classification applications. Some of them are very familiar, which are using chat box, voice assistant. Suppose you have your phone, okay, you have your phone and it has a Siri, and you have a feature called voice unlock. Whenever you press say your voice, the Siri gets activated. How does that work? Because the Siri has been programmed with some audio classification which will tell us that okay, this is the voice which I have to take as the input. So whenever a voice will be go, it will get extracted and it will get converted, and some feature in the machine learning model will take place. Then it will classify that file, and if that classification matches your registered voice, it will unlock. So this is a pretty good technology, right? So this is what we'll be doing, and we'll be seeing some scratch of it. Of course, this is a kind of entry level project. This can have better advancement as we move into different technologies like sound navigation, environmental sound classification, music genre identification is one of the most common, because as you know we'll be passing different music notes, and on the basis of that note we'll be classifying okay, this is a rock music, or this is another type of kind of melody music. So now what we'll be doing in our problem statement as we have given a data set which contains several audio files. Actually, I have downloaded this data set from the Kaggle website. I'll be providing you the link from where you can download it and how to download it. In that, I have a CSV file in which all the information of that file is there, and what is there, and along with the different audio files. So we'll be using those audio files as our independent features, which will be telling us different information. Then the labels will be a dependent feature. With the help of this, we'll be able to predict our model using neural networks. We'll be using neural networks in this project. So now the basic timeline of the project will be, first we'll be loading our files, then we'll be doing some data analysis, then we'll come to data pre-processing part, we'll be preparing our data, then finally we'll build a model. So hello all, and welcome to the next section of our project. So now this is the notebook section. Now previously in the introduction section we have seen that what do you mean by audio classification and what are the applications for it. So now this in this audio section we'll perform it with the coding part and all the different concepts involved in it. So now as written in this project we'll be performing EDA on the audio files using Librosa library and use neural networks to classify different audio files. So now the timeline of the project will be something like that. First we'll be importing libraries and dataset, a little data analysis part, then finally model building. So now where the very first thing is the dataset. Actually the dataset which I have used is from this Urban Sound 8K dataset. You can found this in Kaggle website. Okay, I have provided you the link. If you'll just click here and it'll get directed to a Kaggle platform, and in that it is a pretty big data set, around 6 GB. So you have to download it. You can also download it from that local website of Urban Sound K, but the download speed is very low. That's why I suggest you to download it from Kaggle here. So the download speed will be good, and it will get all the information from it. So now in this file, there are many different files which are present. Let me show you the data files. It will be just 1 second, then we'll get to the data files. See, so this is the data. In that we have a one file called Urban Sound 8K, and these are the different folds in which different audio files are there. Okay, if you want to listen to one audio file, see, this is some kind of dog barking audio file. So this is a dog barking audio file, right? So in this file right here, each and every description of all the files are given. Okay, like which we did in the fold 4 or fold 5. The file is air conditioner. Okay, so this is how we'll classify our data, because we have the data and these are the labels. So this will be helped in classifying our data. Now moving on to our data part. So as I said, this is the download website. It is around 7 GB. So all the different sounds are there. If you want to read about data, the dataset contains 8,732 label sounds, except less than 4 seconds of urban sound from 10 classes. These are the different classes. So these are all the different sounds which are present, and this is the data. Okay. So now moving forward, as you see, you can download the data. Now the importing the libraries, what will be importing pandas, NumPy, IPython display to basically run our audio file in a Jupyter notebook, Seaborn, Matplotlib for visualization, and finally the Librosa library for basically the audio visualization. This is used for audio, sorry, audio visualization. Audio visualization. So now the very first thing is we just have to load our data. Okay, so now in the previous section in some other projects we have seen that how we can basically pre-process the audio data. Okay, so now in this section we'll be doing that. The audio file, the very first thing is we have to read the audio file. How we'll be doing that, we'll be using a Librosa library to basically understand that file into a bit format, into a frame format, or the digital language. Okay, so now I'll be using ipd.audio, basically IPython display, to read my file in the Jupyter notebook, and Librosa library to load my file. So now as you can see, I have loaded. Okay, sorry, Librosa is not defined. Now our file is loaded. Now if I want to hear my file, though this is my file. As we heard, this is some kind of train file. Okay, if you want to select another file, we can always go to the our library, and we can see different file. Let's see, where is our file. This is my root folder. Okay, this is my Jupyter notebook root folder. So I have to search for urban column. It should be here somewhere. See, urban sound, and let's see fold 2, and this is the file. Okay, I'll just copy here and paste the name here. The path is the urban sound in my root folder, then fold 4, then there. Now my fold is fold 2, so I'll just give it fold 2. Here also fold 2. I'll just paste my file. Okay, so now this is my file. So as you see, this is some kind of dog barking file. Okay, now if you want to display using Librosa, so you will just say librosa.display.waveplot. So this is my file. So now as you see that when the dog was barking, see, the bark sound is this, and it was a pause. Then the bark sound, then pause. So this is what the how our library or how our sound looks like in the time domain. Okay, so this is how we loaded our file. So now this is for one file. Okay, we can like load all of the different files, but our main motive is to classify these files. So like this is file for or dog barking, right? So what we'll do, we'll classify it using all the different files. We'll take all the files, the input, and use that CSV file to basically classify. We'll understand all of this, how we'll be doing this in the next section. Hello all and welcome to the next section of our project. So now in the previous section we saw that how we can load the different audio files and what are the different libraries we use. We also loaded a file using the IPython library in the Jupyter notebook. We saw the wave plot using the Librosa library of your audio file. So now what we'll see the urban sound CSV file which was present. Okay, so I'm saying that I'm naming that as labels, and then we'll see that this is the file name, this is the FSID, then start, the endpoint, the fold number, the class ID, and the final, the class. So this is our dependent variable, and the audio is a dependent variable. So what we'll do, we'll extract the features from our audio file and use them and input this variable. Okay, what we'll do, we'll for this audio file we'll extract some feature and we'll say for this feature this is my dependent feature. So by that our model will get trained, a model will get trained, and then it will know that okay, when they'll pass this sound, it will know that okay, this is my sound, so this is the class of that feature. Okay, so now in the next section or in the next part of the video we'll do that. So now as we see, we have seen a labels part, so we have to create a model which will classify what category of sound the clip belongs to. Okay, so for this we'll create independent features that are different time domain and frequency domain features, and different labels that are present, that the labels in the label CSV file. So now in the very first thing we have to do now is to extract audio features. So now I'll be using two different audio features. One is the time domain feature and then is the frequency domain feature. Now zero crossing rate. So now this is an audio feature which is used by different audio processing libraries. What is zero crossing rate? This is the rate at which a signal crosses the negative value to zero and then to a positive value. So now what happens in zero crossing rate, it will tell us the time, okay, at what rate the value or the value is crossing from its zero to from negative to zero to positive. Basically if a audio has a very high pitch sound, it is suddenly goes to deep, that means it has crossed a zero to negative path. Okay, like that. So now what we do, we'll be using librosa.feature.zero crossing rate. Okay, this is a feature in Librosa. What are these two things? Frame size and hop length. So what is frame size? Basically it is telling me the number of samples. If I want to see, I saved my I load my file using the audio. Okay, if I want to see audio dot shape, so I have 88,200 samples. Okay, so now frame size is what, that it will contain around 1024 samples in one frame. Okay, so that is what frame size is. And hop length is basically to overlap the signals. Okay, if we'll only create different frames, there will be certain information or there will be a time gap between different frames. In order to avoid that, we are using a hop length. So I am just passing those parameters librosa.feature.zero crossing rate and passing my audio and frame length and frame size. So when I'll do this, now if you want to see what are my values, so these are my different array values. Okay, now if I'll see the shape, it will be around 0.1024 because we have that much frame. Okay, so now this sorry 173 because 1024 is the frame size. Okay, and we have 173 frames. If you'll divide by, I just write print number of frames produced. I'll just say length of audio divided by 1024, sorry, divided by 1 1024. Okay, sorry. Okay, so number of frames produced are this. Okay, this is exactly a somewhat a similar number. So these are the number of frames produced, and these are the different frame size. So if you want to see, if you want to plot it, okay, if you want to plot, I'll just write plots ZCR dot music, sorry, PLT ZCR. There is some problem. Heck, here you have. So now this is my plot plt.zcr music, and this is showing me all the ZCR values. Okay, so this is what it is. Okay, so now this is the plot, and this is showing me how my rate is changing for the ZCR. So this is what one of my feature. So you might be wondering how we can classify that. Okay, suppose if it is a dog sound. Okay, so what it will do, that dog sound will have a particular ZCR value. Okay, so when we'll say that okay, this particular sound had this particular value, and whenever this particular set of values will come, it will know that okay, this is a dog sound. Similarly, our second feature is Mel frequency cepstral coefficient. So now in sound processing, the MFCC is a representation of short-term power spectrum of a sound based on linear cosine transform of a log power spectrum on a non-linear Mel scale of frequency. So now MFCC coefficients are nothing but these are particular log transform of a spectrum. Okay, these are log transform of the values. Okay, MFCC is a feature. If you want to go deep in it, you can search what are MFCCs, and you'll get all the information. Now we are using a feature called librosa.feature MFCC, because in that librosa only a feature is present. Okay, when you use librosa.feature.mfcc, it will give you all the info, all the different features. Okay, so now as you can see 173, here also 173 or 10, we have selected a number of 10 MFCCs 10, so 10 degrees of MFCCs will be created. So if you want to visualize it, you will just say MFCC is not defined. Okay, MFCC music. So these are the different MFCCs. Okay, there are 10 to that. Okay, 1, 2, 3. These are like 10 orders. Okay, this is my MFCCs. So these are one of my features which I'll be using in order to classify. So now, but this all the things we have done this for a single audio file, but we have to do this for all the audio files and merge it in a data frame, and then we have to assign this value, okay, this value to each of the particular file. So how we'll be doing that, we'll be seeing that in the next section. Hello all and welcome to the next section of our project. So now in the previous sections we have loaded our audio file, we have visualized it, we have listened it, and we saw that how we can extract the different audio features. We saw that the audio feature will be using our zero crossing rate and the MFCCs, that is Mel frequency cepstral coefficients. So now but I told you that the thing which we perform was for only a single audio file. So now what we have to do, we have to do all this procedure for all of the different things. Okay, so for that what we'll do, we'll define a function. We'll say define mfcc dot extractor, and I'll just pass the file name, then I'll say audio and sr, the same thing which I did for this file. I'm just combining it in a single function, audio, and then I'll say mfcc librosa dot feature dot mfcc. Then I'll say okay, scale it, basically that make the mean of it, take the mean of it, and return me those values. Okay, the same we'll be doing for ZCR also. And then what we'll do, we'll just extract this, we'll be doing that for all the audio files. Okay, so for that what we'll do, I'll just create a list called ind features. I'll say for index num row in labels dot iter rows. What it will do, it will iterate through all the rows in my label. What is my label? I'll just say label is my data set. Okay, the data set which I created. Okay, it will iterate through all the rows. It will iterate through all the rows, iterate to all the rows, and it will say for index num. Okay, index num is basically the index number. This is the index number and the row. For index number and the row, it will iterate through all the rows, then it will say I'm getting that file name. What is the file name? Like, I'll just type it here only. So this is my file name. Okay, this is my file. I want to extract this. What I'm saying, os.path.join, or I'm taking, okay, take that path, that os.path.absolute path. Absolute path is basically the defined path which is there at time I am passing my this file. Okay, the urban sound, because in that folder only my all the files are present, right? In this, till that the function it has created to my root folder, now I have to give that path. So urban sound is my path. In that it will look for the fold part. Okay, in the urban sound it will look for fold, then it will say for fold 1 2 3 4, like it will iterate through like for the fold value. Okay, the different fold values. Okay, now and then it will say str.row.slice file name. This is the slice file name. So this is the file name which I'll get. Okay, this is the file name which I'll get. Then I'll say label row class, give me the class variable also. Okay, give me the class variable. So this is my variable. Okay, this is my variable. Then what I'll say, I'll just apply my function to that name. I'll just apply my function to that mfcc extractor to that file name. So it will, what it do, it will perform all the operations. It will perform all the operations. It is saying mfcc extractor is not defined. Okay, I have not defined it. Then also I have to do one thing. I'll just write import tqdm, and then I'll just write here tqdm module object is not callable. Okay, sorry. Now what will happen, what it will happen, it will give all the mfcc extractor. It will provide me, or it will does this function which I have said. What it will load the file, it will create, or it will create the mfcc coefficient, then it will find out the mean of that, and it will return me those values for. So it will do this for each and every file. Okay, and then what I'm doing, I'm appending my this value and my labels. So what will happen, for that, for particular file I have these mfcc values and the label for it. Okay, so now this I am doing the same for my ZCR also. It here also I am saying, okay, print me all the value, give me the same thing I have written here also, and then I am saying ZCR dot extractor. I am giving my file name. I am giving, okay, return me the ZCR values, and for that. So now you can do this for the do part. First you can create the model for the ZCR values, and then you can create your model for the MFCC values. Then you can see, okay, what is the difference in the accuracy. I am creating my model for MFCC. Now it may take some time, because obviously it will iterate through 8732 rows. Okay, so it will obviously take time. So by the time it will get run over, we'll just run into the next section, and in the next section we'll see, after it has run completely, it will give us a list. Then what we'll do, we'll convert that list into a data frame. Okay, we'll convert that list into a data frame. Then we'll just build our model. So now let's move into the next section where it will be completed, and then I'll show you how we can create a data frame, then how we can finally build a model using that. So see you in the next section. Hello all, and welcome to the last and final section of our project. So now in the previous section, what we have seen, that we have loaded an audio file. We have seen what are the different audio features, which were the audio zero crossing rate, that is the rate at which the signal crosses the negative to zero and then to a positive value. And then the next is what was our MFCC. So now what we have done, we created, or we calculated a zero ZCR and MFCCs for a single file. Then we saw that, okay, how we can we created a function for that. Then we said how we can actually do these for all the different files, present. Okay, so now what we did, we created a function. We said it, okay, we gave the path, and we said iterate all through the rows and perform all the mfcc extractor file name, and then give us in a form of results. And the thing is, I did both of them for ZCR and MFCC, but I am actually calculating for MFCC only because it takes a lot of time. It goes to label all of these. Okay, so now you can also do for ZCR and see what is the difference in the accuracy. So now we have what we have. We have a list in which we have MFCCs and label. So now this is the list which is created. So now this has all the MFCCs and the label for it. So for the dog bark, this is the MFCC. Now what I'm doing, I'm just creating my independent and dependent features, that is the MFCCs, and their dependent feature is the label. Now that then what I'll do, I'll just label encode my dependent feature, right? Because I can't just directly feed that into my model, because what is a dog bark, I'll just label it. Suppose there are 10 variables, what I'll say, okay, dog bark is for 1, children playing is for 2. So for that it will have these values, then it will understand, okay, that is of second number, that it will work. Then I'll split my data. I'll just take my 30 to 70 ratio, that is the 30% for test data and 70% for trained data. Then what I'll do, I'll just import all my models. I'm taking my neural network here, that is the sequential model. I'm just taking all the layers. One is the ReLU function and the activation function is sigmoid. I'm just getting my loss function is categorical cosentropy, and matrix is accuracy, and we have an optimizer Adam. So now this is what we have trained our model. Now we have seen that I have written shape 10. Why I have written shape 10? Because previously I told you that I have created an MFCCs of 10 level. Okay, if I would have created the MFCC of, let's say, 40, then it would have been here 40. So this is how create. Now I fitted the model with batch size is 10 and epochs is 100. So as you see, all of my model is getting trained and all of these things. Now it has already getting trained and loss is reduced. Now the my loss was around sorry, the loss was around 8.233. It has been reduced to around 1.4993. Okay, now what I'll do, I'll just evaluate my accuracy. Now I'll say accuracy of my model is this. So now I'll just predict my labels. So now it has predicted. Now this is my model. Okay, this is my model. If I want to see what is my prediction, see, I'll just do the prediction. So now these are my predictions, but right now I don't know what this is, right? So I just have to convert, or I just have to see, okay, what is that thing. So what does this file mean for? For that I have to basically inverse transform the data. So let us try this on a whole different new file. I am saying, okay, file name is urban sound 8. Okay, now what I'm saying, urban sound, this is my, then it will go into the fold, let's say fold 2. Then what we'll do, we'll just go to the fold 2. We'll just go to the fold 2 and we'll just find out. Okay, we'll just go to my urban sound. We'll go to fold 2, then we'll select a random file. Okay, let's say we just select this. Okay, we just select this, then we'll just go again and we'll just print it here. Now if I want to then we'll just print it here, then we'll run this. Okay, we'll run this. I'll just remove this ZCR one. Okay, so now what will happen, we'll just run. Hello all and welcome to the final section of our project. So now in the previous section we have seen that how we build a neural network. On the basis of that, how we build all these things, and how we have fitted our model. And now what we did is how we can try this onto a new audio file. Okay, and we can try how we can try this into a new audio file. So now in the previous section when we had some error. Now the error was that we were calling the same function. We were calling the function which we have created, but now we don't have to do this, because what it was, we created this to do to convert to run in a for loop, right? So what we'll do, we'll just directly do all of those things. What we'll do, mfcc features, that we have the features like librosa dot feature, then we'll create all the mfcc value, we'll just scale them. Then what we'll do, we'll just print all of those features. Then we'll say we'll just reshape them into 1 comma minus 1 so that when feeding into a network it don't get out of shape. Then what we'll do, we'll just predict it. Okay, model dot predict classes. What we'll do, what it will do, it will predict the method. Now after it has predicted, what it will do, we'll just inverse transform the predicted label. Now when you'll run it, you'll see that okay, these are the different labels, these are the different things, MFCCs which are predicted, and this is the label which was there. Okay, and that is for air conditioner. Now when we'll go there, now we have used this file. Okay, now when we'll go to the file, then we'll go to the fold 2. We'll just go to the file. We'll just go to the file and we'll just go to fold 2 and let's see what was that file. That was 102858. 102858. Okay, it is very. So let us find a file that we can understand. Okay, let us go here and okay, this was the file. Let's hear it. This is my fold 2 and this is 1006.52. Okay, let's just find this file here. Okay, 4201. Let's just find this file somewhere here. We'll just go here and what we'll do if there's a difficulty in finding, we'll just copy this file. We'll just copy this file and we'll just paste it right here. Okay, we'll just paste it right here. Then we'll go again and this is our file. Okay, this is our file. Now what we'll do, we'll just go to our data. Then we'll just say okay, give me the file right here. Okay, this is my file. Now what I'll do, now this is also an air conditioner. Okay, now what I'll do, I'll just play that sound. So okay, this was a very short sound. So what we'll do, we'll just find out some another file which we can hear, right? So this is one file. Okay, this is some, I think some gunshot fire file. I'll just copy it and I'll just paste it here, 7064. Now we'll just go here and we'll find that file in our directory. So this is our file. We'll just copy this. We'll go again and we'll just paste this file. Okay, so this is a jackhammer file. Okay, this is basically a jackhammer. When we'll just hear it again. So yeah, that is a jackhammer, right? That is a jackhammer. So you know that how it has perfectly classified that audio file is a jackhammer. Like that, you can classify any of the files, right? Okay, so this is how you do it. Okay, this was a brief introduction of that project, and this is the whole thing. Now what you can do, you can try out in on different files and you can see the classification and all of those things. So I hope you understood all of those things. This data set you can download it from this website right here. It is of around 7 GB. All of the different things are present. All of the things I have told you, okay, what are the different things, what are the different things present. So now what you can do is you can practice this, you can do it on your own, you can do the changes, you can also try out with my ZCR value, you can also try it with the Z with this zero crossing rate and MFCC. These are the two audio features. Now what you'll do, you can just try out with different things, you can try out different models. If you're not neural network, you can also try out different machine learning models and see what is the output. So I hope you enjoyed it.